2 o'clock, so I guess we'll get started. Can everybody hear me okay? I'm going to assume yes. Okay. Good afternoon. My name is Stacy Alisi, and I'll be the moderator for this session entitled Preserving and Understanding the Past Through Large Language Models. Before we begin, I have a few reminders. We have a code of conduct that we will adhere to for this conference. The link will be posted in chat in just a minute. If you have any issues related to conduct, there's going to be an email as well. Please be sure your microphone is muted. The presenters have asked to hold all questions until the end. And then during the Q&A, please wait until you are invited to unmute before asking a question or making a comment. You may also use chat for questions. The session is being recorded. You can enable captions by clicking on the Show Captions button at the bottom of the screen. It is my pleasure to introduce Dr. Chreston Miller and Dr. Bipasha Banerjee. Dr. Miller is an associate professor and data informatics consultant within the University Libraries at Virginia Tech and holds a PhD in computer science. His interests lie in applied machine learning and natural language processing for a diverse range of disciplines such as history, fashion, and food science and technology. Dr. Banerjee is an AI research scientist and assistant professor at Virginia Tech University Libraries and holds a PhD in computer science. Her research focuses on natural language processing, information retrieval, machine learning, and artificial intelligence. And she is passionate about developing AI-driven solutions for all digital libraries. Please join me in welcoming Dr. Miller and Dr. Banerjee.
Okay, thank you, Stacy, for that wonderful intro. Let me go ahead and share my one window I'm trying to find here. Okay. Okay, can that be seen?
Yeah.
Excellent. Well, good afternoon, everyone. Thank you for having us and attending. So I'm Dr. Chreston Miller, and my associate here, Dr. Bipasha Banerjee. We'll be talking about preserving and understanding the past through large language models. And, well, you already know who we are. Stacy did a great job with that. So this slide is kind of just a filler to make us look good, I guess. I don't know. But I do want to go back to the main slide. I want to look at the title again. Do something a little bit different. Look at two different pieces. One is preserving, and we're preserving the past. So what past are we preserving that we're talking about in our project? And we're looking at historical documents from the early 20th century, and we want to be able to understand what's in them. These are real estate documents with vast amounts of information about the history of the area where they came from. So understanding them can be a little challenging because they are scanned documents. You can read through them, but there might be dozens, hundreds, thousands of them. And so we are interested in how can we support this process in actually understanding it and also preserving. So that's where our focus of what's called optical character recognition comes into place. And so this is just to give a nice little overview of what OCR is. We take on the left here, we have a nice little diagram. We have a document that we feed into an OCR engine. And then out the other side, ideally, you have wonderful extracted text that you can do great things with. You can search, you can do any type of machine learning stuff to understand things. But the OCR engine is really important in how you're actually able to do this. Traditionally, there are OCR engines that are trained on patterns, trying to identify what characters look like in an image. There are some that first look for where text is in the image and then goes in for the recognition. And so you have a two-step right there. And lastly, the big one that we're going to be talking about today is multimodal large language models, or LLMs, and how they can reason with images, and actually you can do question answer about them. So this gives you a little example of the type of documents we're looking at. Here are 3 scans. So starting on the left, we have a nice full page paragraphs. However, there is no fading going on. It can be a little hard to read. In the middle, we have another scan where there's some signatures on the bottom, empty space on the bottom left, and some other text that some is faded, some is not. And on the far right, we have what we call inverted, where for some reason the scan has a black background with white text. And not quite sure where that came from, but that was the collection that we got. So as I was saying, we want to apply OCR to these documents. And as you may have seen, there are some challenging factors. There can be poor scan quality due to the age of the documents, which includes different levels of fading. So some of the characters, as we'll have some zoom ins later, the lines can be thin. They could be partially there or part of letters not even there or even missing. And then there's also, depending on how the pages were scanned, there's different levels of skewing. So either to the left or right, but you don't really know ahead of time what it's going to be. And as we saw with the inversion, there's possible variations of background contrast. I've seen some scans that actually have some shadow in there too. So you have a number of different things going on that make performing OCR that much more harder. So we are investigating the use of recently developed multimodal large language models with vision capabilities to perform this OCR on these scanned, they're typed documents. We're not working with handwriting right now. And these are, like I said, from the early 20th century. So why would we perform large language model based OCR? Well, they're using the cutting edge techniques. These are being updated constantly and ideally improving all the time. I mean, interestingly enough, Dr. Banerjee and I wrote a paper, and by the time it went to review, everything had changed almost. More algorithms had come out, and the reviewers were like, "Why didn't you do this?" I'm like, "Well, they weren't out yet." So, and as we observed from our recent experiments, they can be more accurate. However, there are some drawbacks. They do require some specialized hardware. They use video cards called graphic processing units or GPUs, and that can be a little pricey sometimes. And also, it requires more advanced programming, which includes, it can be very involved to set up your environment. So the results that we present today, we are from the LLM Llama 3.2 with vision. And we chose this one because the recent experiments showed it had the best results. Now, at the time of our experiments, which were only like 3 or 4 months ago, there were mainly 3 multimodal ones that were of notable, I guess, to look at. One of them was ID Fix 2, and the other one was OLM OCR, also based off of Quinn. But Llama 3.2 rose to the top to actually be the best. Now, we're also in the process of testing other vision models because, as I mentioned, more have come out. We're in the process of looking at, I think, 5 or 6 other ones on top of what we've already tested. So there's a lot going on. And one thing that's really interesting about Llama 3.2 is you can run it on very cost-effective hardware. And especially, this was really cool when I found this out. If anyone who is familiar with the Kaggle notebook environment online, you can get a free access to GPUs, and you can actually run this model for testing. And that's how I discovered it actually worked for OCR. So in order to make this, worthwhile, see if it works and everything, is we need to create a ground truth data set to measure the accuracy of what we were trying to show. So Dr. Banerjee and I, two researchers, we independently looked through different sets of these documents and identified different clips. We would take clips of like single sentences, short paragraphs, long paragraphs, and us combined, we ended up with 178 of these clips. We came together, we removed duplicates, we ended up with 125. And then we had the fun time of transcribing all of them. And not only doing that, we had to compare our results between each other programmatically to make sure they were the same before we could begin any experiments to see, okay, how good do these approaches, OCR approaches work? So just to give a little bit of background, here is a histogram of the word count distribution of all the clips that we transcribed. So this kind of give an idea of how many short ones there were, how many long ones. So it's a little bit skewed towards the shorter, but we still had a good variety in there in length. And here is a nice slide of some of the examples of these clips. Starting at the top, we have a nice, clear clip of what we labeled as this is normal. Good contrast, the characters are clear, and we don't see any visual challenges. Next is faded, where it can get very interesting. There's different parts of the letters are missing. Some are thin. And so this is one big challenge I've seen in OCR technologies, which I've been working with for about 5 years, seeing very different kinds. And this is a big problem when you have faded. And skewing, as I've seen, can also provide some issues, which is the next one down. In this case, it's skewing to the left. And then we have an inverted skewing to the right below that. And so as you can imagine, we can have inverted skewing faded. We have a whole different variety that could happen. And then we have special characters at the bottom, such as like parentheses, not parentheses, percent signs, division signs. And so I have two examples of some of those clips, and one of them on the left is normal, not inverted background. The one on the right is inverted, but also faded. So as you can imagine, these documents are kind of hard to extract text from, so you can actually get to the understanding part. So as showed the examples of labels, here's a breakdown of the labels of our data set. The main 4 labels we used was normal, faded, and skewed. So here you can see ones that the number breakdown of how many were normal, how many were not, and so on in this table. Then we looked at the combinations of, okay, what the big ones of faded and skewed. And so how many were both, how many were either or, and how many were neither. And then in the right table, table 3, we looked at, okay, what about skewing itself? Because that can cause problems in and of itself. What about left skewed and right skewed and not skewed? So there's a whole bunch of different things we looked at to try to understand, how are these OCR engines actually operating with this type of conditions of the text. And with that, I will pass it over to Dr. Banerjee.
Thank you, Dr. Miller. So in this slide, we are describing the workflow diagram of our pipeline. So as Dr. Miller mentioned, we have 125 clips that both of us transcribed. So we start with those historical document clips that have been scanned and are in PNG format. We pass it to the OCR technology. I've grouped it into non-LLMs, which are basically machine learning technologies, and the vision-enabled LLMs. Within the non-LLMs, we chose DocTR, Surya, and PyTesseract. So we did look into what are the other technologies that exist for OCRs, and our primary concern was to make sure we only use openly available technologies without any paywall. That was the first decision maker of what we chose. And the second was we tried running them, looked at the performance. These are the top 3 ones that stood out. Similarly, for LLMs, we chose openly available for research LLMs with smaller to medium like parameters, which wouldn't require a lot of GPU hardware because we wanted to make sure we can run it on our server. So that went into the decision. Llama 3.2 Vision, IDFix2, and OLM OCR are all vision enabled multimodal LLMs that was chosen for our experiments. Now, once we have the results from each of these OCR technologies, we moved on to evaluating them against the ground truth that we created and to compare how well these models are. For evaluation, we chose 3 different metrics. The character error rate, which is a metric that helps us to evaluate the accuracy of machine-generated text versus like the ground truth by measuring the percentage of characters that were incorrectly predicted automatically by the system. So in this case, a lower CER score means better performance. So a score of 0 is like perfect score. The second evaluation metric is the bilingual evaluation understudy, or the BLUE score, which is a metric that helps to, again, evaluate machine translated text with ground truth. It essentially measures the similarity between 2 pieces of text based on comparing the number of n-grams or sequential groups of words. So that's what BLUE score does. A perfect match is indicated by a score of 1, and a mismatch is indicated by a score of 0. So for BLUE score, higher score is better. And finally, we use normalized Levenshtein distance. So Levenshtein distance is a distance metric which helps to understand the similarity between 2 pieces of text by quantifying the number of single edits between text A and text B. And the normalized version is another way of representing the difference between 2 strings, typically ranging from 0 to 1. With 0 representing ideal strings and 1 representing the strings are completely different. So I wanted to mention this, that CER and NLD, both these metrics, lower score is better, BLUE, high score is better. Next slide, please. So these are the results from our experiments. We compared machine learning models with LLMs, and again, CER scores lower, better, NLD lower, better, and BLUE scores higher is better. There's another column over here, which is the top CER percentage. So CER, again, is the character error rate, and the top CER percentage, what we chose to do is from our 125 clips, we wanted to see how many or the percentage of them that had high accuracy and low error. So the typical acceptable range is 2% of CER error. So 57, so for example, in DocTR, 57.6% of clips had a error of 2% or less, which means 98% or higher accuracy. So for top CER percentage column, higher score is better. So within non-LLMs, we do see that DocTR performed the best, with the exception of Surya in Levenshtein distance, which slightly performed better because it has low normalized Levenshtein score. But between the 2 technologies, LLMs versus non-LLMs, we do see that LLMs, specifically Llama 3.2, outperformed in almost all metrics except for standard deviation in CER, where OLM OCR did perform slightly better. So we do see that from this results that LLMs ended up performing significantly better when compared to machine learning one. Next slide, please. So this is an example of how the LLM performed. So this, as the title suggests, is perfect accuracy. The clip is faded. It's actually slightly skewed to the right, but when you directly look at it, it looks aligned. But the LLM specifically Llama 3.2 was able to give a perfect extraction without any errors. So it is also important to note that in all the experiments that we did not add any data augmentation or changed we didn't perform any data cleanup at this point, because our goal was to set up baselines to see how well out of the box these models are performing. And depending on what we find, we would do next steps of, okay, we'll do more data augmentation, cleanup, all of that. So Llama 3.2 did very well in extracting text from slightly faded content. Next slide, please. This is also another example of perfect accuracy where the clip was inverted, which means instead of the traditional white background, black text, we have black background and white text. And that didn't seem to cause any issues when we were implementing OCR technologies and trying to extract text. So this again gave us perfect extraction. Next slide, please. This is something interesting that we noted when we were looking at the results, and we didn't expect this. So there are two highlighted portions of the text in the clip. The first one being the end part of the previous sentence, and the second one being a hyphenated word because the sentence was broken into 2 lines. Now, if you look at the extractions, so the LLM ended up excluding the first highlighted portion in the clip, the or not part, and it also ended up making ownership a single word. Now, this is something we hadn't expected because when we were transcribing, we transcribed as is. That was the clip, that is a transcription. But it's interesting to note that the context, LLMs were able to learn from their training material and understand the context, and they kind of corrected it in itself. But do we want that? That's the question. Like, is this good or bad? We were quite conflicted. This is good. Yes, ownership should be a single word. It shouldn't be hyphenated, but we are trying to extract text as is. So this is something that was interesting and stood out to us, and we wanted to point it out. Next slide, please. This is a slide where we do see complete errors. For example, this particular clip is quite faded. Number 9 was extracted as character Y, and the spelling of Johnston was completely wrong. So the results that we showed in the previous table, these kind of errors have been accounted for in the results. So our next step is to make sure that we can improve the scores and account for such challenges that we encountered in our data set. Next slide, please. So this brings us to what are the benefits of using LLMs with vision? Clearly, LLMs with vision ended up performing the best. So we wanted to discuss how it's been useful. We were able to perform OCR on the original scan documents without any visual cleanup. So as I was mentioning, we did not touch those clips. We just used the original clips and sent it to the OCR technology. So we did not change any background contrast, and all the results were based on the original clips itself. So the models did end up performing decently, and we didn't expect it to be this good out of the box. Vision LLMs such as Llama 3.2 and the other models that we mentioned are all freely available to use with no paywalls for academic research. And this was very important to us because we want to be able to use these models on our servers. We don't want to interact with APIs and have greater control over how we use the model inherently, because we want the model to extract text and not generate text, no hallucination. We want it to be verbatim. To have that greater control, we wanted to be able to computationally access all those models, have access to the model weight. So this was really important to us. Next slide, please. I also mentioned that we chose to run the smaller version of the multimodal LLMs. This was a conscious decision because we wanted to run it on a cost-effective hardware. And we were able to run all of these models on, it needed GPU, yes, but it wasn't very sophisticated GPUs that we hear larger models requiring. So it was able to run on modest GPU requirements, and thus it helped us avoid high equipment costs. And we also do see that because we were able to run on our local servers, it will be available to a wider range of libraries with varying technological budgets. So this would be easily useful for other libraries, be it academia or not academia, to be able to use this technology and extract text. Next slide, please. So yes, we did extract the text. What do we want to do with the text? Why is it important to extract text? So as Dr. Miller was mentioning, we are also trying to understand. So the first step was extracting the text, but it will move on to understanding the history. And OCR is something that enables us to do that. Being able to use LLMs for OCR greatly enhances text extraction for researchers, and in turn helps us analyze text and apply many machine learning and natural language processing on that text to understand more. So thus, it allows researchers to perform text analysis as well as preserve content that would otherwise be like physical content in our libraries in form of books and maps and all such digital content. All such physical content that are now computationally accessible because we extract the text and make it available. So this is especially true for large document collections. So our digital library platform has about 40 terabytes of data, from handwritten letters to maps to newspaper collections. So being able to extract text from them within our servers helps us make content more accessible to our patrons and stakeholders. Next slide, please. So something that we are working on, Dr. Millen and I have been working on, is to scale up the workflow to run extraction on the entire data set, because right now we do have clips. We want to run it on the entire page. Apart from that, since we want to fine tune these multimodal vision LLMs in the future, in order to do so, we need some augmentation, because right now our challenging clips, we have like limited number. We want to balance that data so that we can train our models. So we are in the process of developing an augmented data set with to help with data imbalance issues. And once we are done, we are also working on other OCR technologies that have been developed since then, as Dr. Miller mentioned. So that's also something that's ongoing right now. And I think that's about it. We are open to questions. Chris, yeah, next slide. Thank you.
There are some questions in the Q&A. I don't know if you can see them, or I can read them. Whatever's easier for you. Can you see the questions?
I can see them.
Oh, yeah, there they are.
In the Q&A, yeah.
Okay. Actually, Stacy, if you wouldn't mind just reading them out.
Sure. Kiri Wagstaff, I hope I'm pronouncing that correctly, said great examples. It looks like you may have some with marginalia as well. Is that true? And how did you handle it?
Well, actually, specifically for the LLMs, all we did was give it a clip and ask it, please identify the text. And it gave us the text. And so we didn't have to worry about adjusting anything. We just wanted to see how it worked, as Dr. Banerjee said, out of the box. And so, I don't know, Dr. Banerjee, do you have anything else to?
Yeah, I just wanted to add that since Chreston mentioned the prompt, I would want to say that we did have to work on the prompt quite a bit. For some odd reason, when you say, please extract text from this document, it starts giving you more explanation about the document after extracting. So we did work on it, and we found that the prompt which says perform text identification of all type text and punctuation in a single line verbatim work like magic. So we made sure we had to like include the word verbatim. And we did also add, please don't provide any explanation or paragraph numbers so that it extracts the text as is. In terms of text from the margins, we did not encounter any issues. But as Dr. Miller says, we did not either, like we did not do anything with the data to not encounter this issue. So we're assuming the clips in itself were clean enough that the model was able to just realize that this is typed text and I should only look at typed text. Yeah, that's what I have.
Okay, the next question was from an anonymous participant. Do you anticipate this will be the future of archiving in libraries? Historical text versus transcribed text side to side from using LLMs?
Well, this is something I've been thinking about for a while as I've been working OCR in the libraries, especially working on OCR of challenging text. I would like to see this become part of the workflow of archiving in the libraries, especially since the technology is here. It's becoming more and more accessible. And with our experiments, we're showing that this actually is feasible, because I know traditionally with other non-LLM OCR engines, there was some expectation that you perform cleanup, not all the time, but perform some image cleanup. And Dr. Banerjee mentioned that. And one challenge with that is you don't know what you have to clean up ahead of time, especially if you're dealing with hundreds of scans. So we wanted to see, as you know, I feel like I'm just repeating myself, what would happen if we just did it on the original scan? And so, and the second part of the question, transcribe text. Let's see. Do you have anything to add, Dr. Banerjee?
So from the one thing that I kind of stood out from this question was historical text versus transcribed text side to side. So not in this collection, but I have been working on other digital collections as well. But the idea is to have the text and the extracted text side by side so that we can kind of imagine if a user is searching for a particular phrase, you show them the phrase as well as the location of that phrase in the document. So that is something that I am actively working on. And that part includes handwritten letters, like Civil War era letters. So stay tuned, I guess that's the answer for that.
Okay, let's move on to the next question from Doug DeChow. Given that it can be a challenge to set up these workflows, are your scripts available on GitHub?
Not yet. But now this is something we would like to. We're in the process of publishing this, so we want to keep things as anonymous and closed right now. But we do want to have those things available so other people can not only take advantage of it, get some really good use out of it, but also add to it for their own specific cases. Dr. Banerjee?
Yeah, that being said, I do agree that setting up those workflows, especially the environments, could be really challenging. And that's something that Chreston and I, we have talked about, and I think we will be pushing those as well in form of a requirements.yaml or requirements.txt so that users know which packages, exactly which versions that we use so that they can computationally like reproduce those kind of results. So we do have it in our private GitLab at this moment, but as Chreston said, once we are near to publishing something publicly, we will open those up too.
Thank you. Tamara asked, you mentioned maps in your collections. Have you experimented with these tools using historical maps? And if so, how well have they been able to transcribe the labels?
I can take this question. Excellent question, because MAP is a collection that I've been working on with our digital library team over here. Our product manager, Jennifer, and I, we have been looking into maps, specifically not only just extracting from within the map, but also from the borders of the map, because those are USGS maps that we have in our collection, which has been digitized. And we are trying to see if the borders of the map, because they do have latitude, longitudes, other stamp, location, all of those information, if we can not only extract, but to classify them so that we can help in expediting some of the metadata creation process as well. A couple of challenges when working with maps are typically very large. So that has been one of a challenge. We kind of mitigated it. So this spring, I've been working with 2 students and they were actively working on the map collection. The mitigation was we had to tile those maps into smaller sections, smaller sections, and based off of each of the section, we were able to extract the text. It's been performing well. The reason is initially we did have issues with text that was not horizontal. If it was an angle, it would miss. But the idea is to extract at different angles, and that was able to kind of take care of extracting text which are at an angle. For example, if it's a river, so we were able to do that pretty well. Now, I didn't include most of it here because we are still evaluating how well it is before. We don't want to say this is good without actually doing the evaluation, but this is something I'm passionate about, yes.
Okay. Mary asks, how is the Llama 3.2 support some specific language? For example, the Chinese traditional language.
Well, in our current experiments, we were doing English because that's the data that we had. Now, I believe, now correct me if I'm wrong, Dr. Banerjee, but I believe Llama also does Chinese, but that's something I would have to investigate.
Yeah, I'm not too sure if the vision models have been trained on different language texts. I know that original Llama is able to do has the support for multiple languages, but that is a text only version, so I'm not really sure, Stacy. Sorry, Mary. You can send us an email. We can look into it and get you an answer. I'll type my email in the chat.
Thank you. Kira asked a follow-up. Can you share a link to your paper or other source for more info on this work? It's very interesting.
I would love to do that when it's published.
Fair enough.
So that's the unfortunate thing with this kind of research and everything is you gotta we want to make things public, but we have to get it peer reviewed, accepted, and everything, and then we can let it see the light of day and know who it is by.
Thank you. Ki Young asks, how do you handle decorative images in the documents? And also, do you plan to apply this to newspaper article, which includes photos?
Dr. Banerjee, you want to take this one?
Sure. So in this work, we only looked at historical documents, but I have worked on newspaper pages from Montgomery newspaper collection. We did encounter some issues, but when it comes to photos, so for the newspaper collection, the use case was only to extract text. I wasn't using the photos or asking the LLMs to describe photos. The main challenges with the newspaper are where the quality of the scans, number one, because some of them, the pages were like cut. I cannot generate content from something that doesn't exist. So that was a huge problem. But apart from that, layout was an issue. But in our recent experiments, we have been able to work on these layout problems because newspapers, again, they are not rectilinear text. They are column and they might have images in between. So that could be a challenge, but we were able to use layout-based models to help detect the layout and then do the extraction, like a 2-step process. When you talk about decorative images, I don't have a clear answer because, again, we were not extracting from those images in that particular use case. So I wouldn't know what to expect, but overall extraction did work in newspaper articles.
Thank you. Hillary asks, have you done any experimentation or seen studies of LLM experimentation on bilingual archival documents? Context, I'm in Canada, where all federal documents are in both official languages.
That is an interesting question, but unfortunately, we haven't run across that yet in our data set. And so that, I guess that would be basically asking the LLM, please extract the text. Oh, no, not extract. Identify was actually one of the key words to use. Extract didn't do anything, which was weird. But you have to, in that case, I would imagine, at least I would try identify the English text and also look at the French text or whatever the other text is. And I actually interacted with a faculty member recently who was doing this with Russian. And so I was working with her to see, how well it would extract Russian text. And so unfortunately at the time we didn't have enough time to finish it. Because we're out of the workshop and we're discussing and only so limited time. Anyway, Dr. Banerjee, do you have any thoughts?
So while you were answering, I wanted to look up the multimodal capabilities of or multilingual capabilities of these models. I could verify that the text version is trained on multilingual modality, and French is one of them, at least for Llama 3.2. Again, I'm not sure about the vision part. I didn't find an answer that if it's an image, is it able to do the same for different languages? But if it's just text and you're using, it should be able to, according to the documentation. At least they say English, German, French, Italian, Portuguese, Spanish, and Thai. I don't see Mandarin though.
Thank you. Jenny asks, well, she says, I'm intimidated by the evaluation methods that you use. Same. Does that require some coding? Where can I learn more?
I guess I'll take that one since I'm the one who coded it. Actually, the three metrics that we used are from one Python library. I think it's one. No, there's two Python libraries. One is developed. I think it was developed by Hugging Face. At least that's where the repository is, I believe. But if you just do an internet search for those metrics and the language Python, those would probably be some of the top hits. Dr. Banerjee, are you verifying that right now? It looks like
I'm then like pasting one link which talks about the character error rate. So yeah.
Yeah, I don't see any more questions. So thank you very much. If you can put maybe your email addresses in chat so people can grab those if they want to follow up. It'll also be available on the Gale site as well. Well, thank you guys very much. It was a really interesting presentation. I appreciate it.
thank you for having us.
Thank you.